Hello students, a very good morning to all of you. How are you? This is our channel, Physics Gallery, Ashavino. Okay, and in the last class, we were discussing about the force between two parallel current carrying conductors in the first section, and in the second section, we were discussing what happens when a current carrying coil is placed in uniform magnetic field. Okay. There we have discussed when a current carrying coil is placed in uniform magnetic field, the net force acting on the coil becomes zero, but there a torque acts and the torque tau is equal to IAB sin theta for one turn, NIAB sin theta for several turns, n turns, or M cross B for one turn, N into M cross B for n turns. MB sin theta for one turn, MB sin theta into N for n turns cross product. Okay, where M is the magnetic moment. Okay. So today we are going to, in the board there is a figure, there is a name, moving coil galvanometer. Today we have to discuss a device, the second device in this chapter which we have to study in detail. Which was the first one? Yes, you have said it was cyclotron. And today we are going to the next device which we have to study in this chapter called as a moving coil galvanometer. Okay, and this is the purely based on the last topic we have studied, torque acting on a current carrying coil. So we are going to discuss about a device called as the moving coil galvanometer. A figure is given, we will discuss that. Okay, so at first, this is a device. Any device has its own use. Okay, so what is the use of a galvanometer? What is a galvanometer? All of you know galvanometer is a device which is used to detect the presence of current. Which is used to detect the presence of current, not to measure, to detect the presence of current. So here also the device is galvanometer, so it is used to detect the presence of current in a circuit. Okay, and its name is correctly moving coil galvanometer. Why? Because the galvanometer consists of a moving coil, a coil. Now we are going to the working principle of the device. Working principle. What is the working principle that we have studied in the last class? What happens when a current carrying coil is placed in uniform magnetic field? A torque experiences. The torque acting, what is the working principle? The torque acting on a current carrying coil. A current carrying coil placed in uniform magnetic field. Okay, what is the working principle? The torque acting on a current carrying coil placed in uniform magnetic field. Okay, now we are going to the construction. The next part is construction. And the figure is given as such. Listen. So, this is all about our moving coil galvanometer. We have opened the galvanometer and had seen like this. Okay. At first, there is a green cylinder. And the green cylinder is a soft iron cylinder. It is a soft iron cylinder. Okay. We will discuss what is its purpose. Surrounding this soft iron cylinder, we have seen a blue box. Okay. And it is a rectangular aluminum frame. What is this blue box? This is a rectangular aluminum frame. Commonly taken frame is of aluminum. Okay. Rectangular aluminum frame. That is the soft iron cylinder is kept inside. It is enclosed inside the aluminum frame. Okay. And surrounding this blue aluminum frame, blue shade which I have provided. Okay. Insulated copper wires. These black wires are copper wires. Insulated copper wires. So what are these? These are insulated copper wires. Copper wires are wound over this rectangular aluminum frame. Okay. It is wound over this rectangular aluminum frame. Many turns, several turns. I have taken 2 or 3 turns around, but there are several turns. There may be several turns. Okay, so a soft iron cylinder is enclosed in a rectangular aluminum frame, which is surrounded with insulated copper wires, and one end of the wire is connected to a spring. One end of the wire is connected to a spring, and the spring is made up of, the spring is very thin, made up of an alloy phosphor bronze alloy. The spring is made up of the spring is a thin phosphor bronze alloy, made up of phosphor bronze alloy. Okay, and the other end of the wire is connected to a mirror. This is a mirror. Okay, what is the purpose of mirror? To look face when we got tired? No. Okay, there is a plain mirror which is connected to like this. Now, all of this arrangement is kept between. We had written here a north pole, and here we have taken a south pole. This is south pole. So there is a magnet, electromagnet or horseshoe magnet, whatever may be. So this is the north pole and this is the south pole of a magnet. That is, magnetic field lines are moving from north to south, which is indicated by red arrows, red lines. Okay, that is the purpose of soft iron cylinder. Now we will discuss. Soft iron cylinder concentrates this radial magnetic field provided by the magnet, and also increases the effect of magnetic field. It concentrates the magnetic field towards the copper coil. What is the purpose of soft iron cylinder? Soft iron cylinder concentrates the magnetic field towards the rectangular turns, copper turns. Clear? That is the purpose of soft iron. And then all of the arrangement is taken in a wooden box with the front glass windows, leveling screws and everything. This is all important. So the construction mainly consisting of, so what you have to write here? Construction. Moving coil galvanometer consisting of an aluminum rectangular frame, inside which a soft iron cylinder is kept. Surrounding this aluminum frame, copper insulated wires are taken of several turns. Okay, and one end of it is connected to a thin phosphor bronze alloy spring, and the other end is connected to a plain mirror. The whole arrangement is kept inside the strong magnetic field of a powerful magnet. And the soft iron cylinder is used in order to concentrate these radial magnetic field provided by this magnet. Okay, then the whole arrangement is kept inside a wooden box with the front glass windows. And the thin spring also contains a needle, which we do not draw here. Contains a needle which passes over which scrolls over a meter. The thin spring also is connected to a needle which scrolls over a meter. Okay, which shows the deflection. Okay, so this is the common structure of a moving coil galvanometer. In NCERT, a cross section of this is given. That is, they have cutted this moving coil galvanometer like this, and a cross section is given. If you want the figure, you may take that figure also. Okay, now I have taken this figure in order to analyze each and every things in the construction. In NCERT, a cross-sectional figure is given and is provided the topic. Okay, so construction is over. Now we are going to the working. You have to write the construction, dears. Okay, so now we are going to the working. Once more, do you want the construction? Once more. The moving coil galvanometer consisting of a aluminum frame, inside which a soft iron cylinder is placed. Surrounding the aluminum frame, there is several turns of copper insulator wires, whose one end is connected to a thin spring made up of phosphor bronze alloy, and the other end is connected to a mirror. The whole arrangement is kept inside the strong magnetic field of a powerful horseshoe magnet or electromagnet. And soft iron cylinder is used to concentrate this radial magnetic field provided by the magnet. Okay, and the whole then setup is kept inside a wooden box with the front glass windows, The spring also contains a needle which scrolls over a meter. Here there is a needle which scrolls over a meter. A needle which scrolls over a meter like this. Okay, the needle is connected to the spring and it scrolls over a meter. Then we show the deflection. We know the deflection. Okay, now we are going to the working. Okay, so what is this device? This is a galvanometer. What is the purpose of a galvanometer? To detect the presence of current in a circuit. So, in order to find the current in a circuit, whether galvanometer will be placed anywhere else? No. At first step, you have to put this galvanometer into the circuit where you have to detect the presence of current. Okay, that is, we will connect this galvanometer to the circuit where we have to detect the presence of current. So, when the galvanometer is connected to the circuit, if there is a current in the circuit, that current will begin to flow through these rectangular copper wires. Clear? When the galvanometer is connected to the circuit, if the circuit contains a current, if there is no current, no change in the position of this galvanometer, or no change in the deflection, any deflection in the needle. Okay, but if there is a current, that current begins to flow through this copper wire. Okay, now the copper wire becomes rectangular coils placed in uniform magnetic field. What happens? Net force becomes zero, but the torque begins to act. So when the current passes through the coil produces a torque, and the torque in the coil becomes NIAB, sin 90. Sin 91. In the previous class, we have discussed it in detail. Okay, so torque in the coil is NIAB, sin 90. N turns, I current, A is the area of the coil, and B is the magnetic field provided by the magnet. Sin 90 perpendicular. Current and field are always perpendicular here. Okay, clear? So due to this torque, what happens? The coil begins to rotate. When torque creates in this coil, listen, come with me. When torque creates in this coil, what happens? The coil begins to rotate. This region into and this region out. The coil begins to rotate. When the coil rotates, one end of the coil is connected to the mirror and the other end is connected to the spring. This is spring. What is this? Spring. Okay. So when the coil, these black lines rotate, the mirror also rotates in the same sense. The spring also rotates in the same sense. Okay. But the spring has certain restoring torque. The spring develops certain restoring torque. What is the specialty of spring? It is an elastic material. It is an elastic material. When you take a rubber band in your hand and begins to stretch it, as soon as you stretch it, a restoring force develops in the rubber band which tries to make it in the original position. That is, when you loosen your hand, what happens? The rubber band comes to the initial position. Why? Because rubber is an elastic body. It has a tendency to regain its original shape and size. Similarly, spring is also an elastic body. When you stretch a spring and on releasing your hand, what happens? It comes back to its original position. Because spring is an elastic body, it gains a restoring force when an external force is applied on it. Clear? Similarly, now the coil rotates. As the coil rotates, the mirror attached to the coil also rotates. There is nothing restoring torque there. Why? Because it is a normal body. Okay. But the spring also rotates along with the rotation of the coil. It is correct. But as the spring rotates, a restoring torque develops in the spring. Okay. And the restoring torque develops. Restoring torque in the spring is given by the equation. Torque in the spring is given by the equation K phi, where K is called as the torque constant or coupled constant or coupled per unit twist. That is a constant related to the spring. And phi is the angle of deflection occurred in the spring. In order to analyze this, one more thing. What was the equation for force or restoring force which we have studied in your +1 topic? F is proportional to x, F is equal to kx, restoring minus opposite direction. Restoring force, this is a constant k and this is the displacement. When a torque acts, torque to, x becomes angle phi and this becomes k. Okay, constant k. And k is now, there the k was called as the force constant, here the k is called as the coupled constant. Here k is called as the coupled constant or coupled per unit twist. Okay, that is, listen, the torque in the coil is NIAB sin 90, which we already know. But due to the torque obtaining in the coil, the spring also begins to rotate. As the spring rotates, a restoring torque develops in the spring, which is given by the equation K phi, where phi is the angle of deflection of the spring, and K is the coupled constant, commonly called as coupled per twist. Coupled constant or coupled per twist. Okay. So listen, the coil rotates, the spring also rotates, and finally the restoring torque of the spring balances the torque of the coil. After some time, what happens? After some time, we can see the torque on the coil is balanced by the torque on the spring. Okay, after some time, the torque on the coil is balanced by torque on the spring. Don't you understood? Just like take a rubber band or take a spring. Stretch the spring. You can stretch the spring by applying external force. As you stretch the spring, restoring force develops in the spring. And can you extend this or can you apply the force after a particular limit? No. After a particular limit, that is maximum stretching, thereafter on applying the force, what happens? The spring may either break. It doesn't stretch. It breaks. Okay, it breaks. Otherwise, you have to stretch it up to a particular limit only. You have to stretch the spring up to a particular limit only. And at that limit, we can say the force applied by you is equal to the restoring force developed in the spring. Similarly, the coil rotates because current begins to flow through it when it is connected to the circuit, and the coil becomes current carrying coil placed in uniform magnetic field. Torque acts and the coil rotates. Since the spring is connected to this coil, the spring also rotates. But the spring when rotates, it develops certain restoring couple. Initially that couple is the restoring force, restoring torque. That restoring torque is small, so it rotates. But as the rotation of the coil increases, the restoring torque in the spring also increases. And finally, the restoring torque in the spring balances the restoring torque in the coil. Then what happens? The deflection stops. That is, the coil stops at a particular angle. The coil stops at a particular angle. Okay. So, where of this much topic? Hoping all of you have written that. So, now we can see the torque in the coil. What is the equation for the torque in the coil? NIAB sin 90 is 1 is equal to the torque of the restoring torque of the spring. Okay, or I will write I is equal to K phi by NAB. K phi by NAB. Now, what is K? K is the coupled per twist of the spring. Okay, N is the number of turns. A is the area of cross section or area of the coil. Not area of cross section, area of the coil. B is the magnetic field. All of these are constant. I is equal to a constant G into phi. I is equal to a constant G into phi, where G is called as the galvanometric constant. Galvanometric constant. Clear? And now I is proportional to phi. That is, if there is current in the coil, if there is a current in the circuit, that current begins to flow through the coil. If there is current in the coil, a small deflection occurs. If the current is larger, deflection will be larger. That is, this spring is deflected to an angle phi, and finally the needle is connected to the spring which scrolls over the meter. So it is deflected, the needle deflects and it scrolls over the meter. That means if there is a current in the circuit, that current flows through the coil. And as the current flows through the coil, the needle deflects. Okay, that is, if there is no current, no deflection. If there is small current, small deflection. If there is large current, large deflection. And hence, we used a galvanometer, moving coil galvanometer, to detect the presence of current. Okay, G is constant because K is the constant of the spring. N is the number of turns, the number of turns of the coil. It is constant. Area of the coil is constant. B is constant. Everything is constant inside the galvanometer. So this is called as the galvanometric constant, or we can say I is proportional to phi. Clear? Okay. So this is the purpose of a galvanometer. And a good galvanometer will be highly sensitive. A good galvanometer will be highly sensitive. Even a very small amount of current may be detected by the galvanometer. So we are going to the sensitivity of a galvanometer. Sensitivity of a galvanometer. Moving coil galvanometer. At first we are going to current sensitivity. What is current sensitivity? That means the galvanometer must show a large deflection for a very small current. A large deflection for a small current is called as the current sensitivity. What is current sensitivity? A large deflection for a very small current. When a small current flows, a large deflection has to be obtained. So this ratio is called as the current sensitivity. From this equation, tell me what is phi by I, NAB by K. That is greater the number of turns, area of the coil, and magnetic field, and lesser the K value. What happens? Sensitivity will be high. The sensitivity, current sensitivity will be high. Even though as the number of turns increases, the current sensitivity increases, but we do not generally take the large number of turns because, why? Because as the number of turns increases, there is a tendency to increase the resistance, which decreases the effect. Okay, so generally increasing the area and magnetic field or decreasing K. In order to decrease K, we have taken the thin phosphor bronze alloy. Okay, and the second one is voltage sensitivity. The second one is voltage sensitivity. That is a large deflection for a small voltage. We know large deflection for a small voltage is IR itself. A large deflection for a small voltage is called as the voltage sensitivity. Phi by I is NAB by K itself. Then resistance also. Okay, clear? So this is the current sensitivity and voltage sensitivity. Clear? So now we have detected the presence of current by using the galvanometer. Also now we know what is the sensitivity of a galvanometer. One more thing. In the figure, in the structure, construction, we had taken a mirror. What is the purpose of this mirror? In order to see our faces when we got tired after doing our practicals. That is the purpose of the mirror here. Is it? Never. You may look on your face also, but it is a small mirror. So, what is the purpose of this mirror? The mirror is used for a particular arrangement called as the lamp and scale arrangement. The mirror is used for a particular arrangement called as the lamp and scale arrangement. What is this lamp and scale arrangement? That is, we had taken phi is proportional to I. We had detected the presence of current, but what is the angle of deflection? What is the correct angle of deflection? We don't know what is the correct angle of deflection. In order to find the angle of deflection phi, we use the arrangement called as the lamp and scale arrangement, and for that arrangement we have put a mirror here. Okay, what is the thing? The thing is very simple. At first you have to put a meter scale in front of the mirror. We put a meter scale in front of the mirror. 1 meter away from it. That is, from this mirror, a meter scale is kept 1 meter away from it. Okay. Initially, the galvanometer contains no current. There is a light source. From that is lamp. From that lamp, light falls onto this mirror and reflects back to the scale. There is a scale in front of the mirror, and suppose from the light source, the light falls on the straight mirror and reflects to a point here. Suppose this is the position of the reflected light at first. Okay. After some time, the galvanometer is connected to the circuit. Suppose the circuit contains the current. That current flows through the coil. The coil begins to rotate. The spring also begins to rotate till the restoring torque in the spring balances the torque in the coil. Okay. That is, at that condition, the deflection stops. The mirror deflects by the same angle phi. Now, the mirror is deflected by an angle phi. Earlier, the mirror was plane. But now, the mirror is deflected by an angle phi because the current carrying coil undergoes deflection. Okay, clear? And the same light, that is, the same lamp, produces the same light. And that light falls on the deflected mirror. And the reflected light falls on another position in the scale, meter scale, which is placed 1 meter away. Is it clear what we said? At first, take the position of the reflected light on the scale. Okay, when there is no current in the coil. Second, take the position of the reflected light in the same scale when there is a current in the circuit. That is, the reflected light is due to the deflected. The reflected light, R-E-F-L-E. The reflected light is due to the deflected mirror, D-E-F-L-E. Clear? Deflected mirror. Okay, surely the position will be shifted. Initially the position of the reflected light was X, now it becomes X dash. Take this shift yes. Okay, shift. If you know shift yes, this is the shift. Shift yes by 2D radians will be the angle of deflection, where D is the distance of meter scale from mirror, which is taken as 1 meter. Okay, so what is the purpose of the mirror? In order to find the angle of deflection, we use this mirror by using a lamp and scale arrangement. In the arrangement, we put a meter scale 1 meter away from the mirror. Initially, we will notice the position of the reflected light on the mirror when there is no current in the circuit. Then, when there is a current in the circuit, that current flows through the coil also, and the coil undergoes a deflection, the mirror also undergoes the same deflection. Then we will take the position of the reflected light from this deflected mirror and take that position. If both initial and final positions are known, we will take the shift of the reflected light. If S is the shift of the reflected light, then S by 2D radians will be the angle of deflection, where capital D is the distance between the mirror and the scale, which is taken as 1 meter. Clear? Okay. So thus we find the angle of deflection also. And from here, we will go to one more term called as the figure of merit. The figure of merit. Finally, the figure of merit of a moving coil galvanometer. So what is figure of merit? A good galvanometer may sense a very slight, very small current also. Okay, listen. Figure of merit is defined as the amount of current passing through the coil. The amount of current passing through the coil, which causes a shift of 1 millimeter. Listen, we want a shift of 1 millimeter in the scale. The amount of current passing through the coil, which causes a shift of 1 millimeter. on a scale which is placed 1 meter away from the mirror, okay, is called as its figure of merit. So what is figure of merit? It is the amount of current, okay, it is the amount of current which causes a shift of 1 millimeter on a scale which is placed 1 meter away from the mirror, clear, which is placed 1 meter away from the mirror, okay, and it is always measured in small current, mu ampere per millimeter. Figure of merit is always measured in mu ampere per millimeter. So what is figure of merit? It is the amount of current passing through the coil which causes a deflection of, which causes a shift of 1 millimeter on the scale. That small amount of current which causes a shift of 1 millimeter on the scale placed 1 meter away from the mirror. Okay, and it is generally measured in mu ampere, small current, mu ampere per millimeter shift. Clear? So this is the working of a moving coil galvanometer. We have discussed the working in detail. In the next class, we will go to the remaining topic of moving coil galvanometer. Okay, so see you. This is our channel. This is Gallery Ashabinu. In the next class, we have to continue the topic. So study well, stay well. Okay, see you.